Hello everyone. Welcome to SHR Trinity. In our previous video, we explored zero-shot prompting. Today, we advance to the next critical technique, few-shot prompting. In this video, we will cover the foundational interview questions on few-shot prompting, explaining how providing just a single example can drastically improve a model's accuracy and format adherence. Let's get started. Before we begin, if you're looking for practical, industry-oriented training in artificial intelligence and generative AI, SHR Trinity offers a comprehensive 30-hour training program. For complete course details, check the description below. Now let's begin today's interview session. We will now begin with the interview questions for few-shot prompting, Part 4, Advanced Concepts. Moving on to our next question, what is few-shot chain of thought, few-shot COT, and why does it boost complex reasoning?
Welcome everyone. Today we are diving into few-shot chain of thought, or few-shot COT, and why it revolutionized complex reasoning in large language models. Normally, standard few-shot prompting just shows an input and a final answer. But for complex logic, that direct mapping fails because the model tries to leap to the conclusion without doing the math first. Few-shot COT fixes this by including intermediate reasoning steps inside the example demonstrations. Why does this work so effectively? Well, transformers process text token by token. By forcing the model to output intermediate reasoning tokens, sometimes wrapped in thought tags, you are effectively giving the neural network more computational cycles to process the logic before making its final prediction. It allows the model to decompose difficult mathematical, logical, or symbolic problems into smaller, sequential steps. When designing prompts for complex tasks, a very common mistake candidates make is only providing the final output in their few-shot examples. If you don't show the model how to think, it won't know how to break down new queries. That's why few-shot COT is considered the state-of-the-art baseline for complex benchmarks. Let's walk through a concrete example. Suppose we ask, Roger has 5 balls. He buys 2 cans of 3 balls. How many balls does he have now? Instead of giving an exemplar that says, answer, 11, our few-shot COT prompt demonstrates the reasoning. First, calculate the balls in cans, 2 cans times 3 balls equals 6. Then add the initial balls, 5 plus 6 equals 11. Therefore, answer, 11. When the LLM sees this breakdown, it mimics that exact step-by-step evaluation process for whatever new problem you throw at it.
Moving on to our next question, how does self-consistency sampling improve accuracy when combined with few-shot COT?
Now let's discuss how self-consistency sampling takes few-shot chain of thought to an even higher level of accuracy. When you run a single generation, even with a great COT prompt, the language model can still make a stochastic error along the way. A tiny mistake in step 2 can completely derail the final answer. Self-consistency solves this by turning decoding into a democratic process. Instead of using greedy decoding at temperature 0, we bump the temperature slightly higher, say to 0.5 or 0.7. This encourages the model to generate 5, 10, or even 20 distinct reasoning paths for the exact same prompt. Even though the intermediate paths and wording differ, correct logical trajectories tend to converge on the exact same final answer. By taking a majority vote across all generations, we effectively filter out individual, random reasoning errors. Think of it as an ensemble method built directly into the decoding phase. A major mistake engineers make is relying on a single output for mission-critical tasks like financial calculations or automated code synthesis. While self-consistency requires more API tokens, the reliability gain is massive. To visualize this, imagine asking the model to solve a complex coding function logic. We generate 5 separate COT solutions. 4 of the outputs reason through the edge cases slightly differently but all arrive at return x plus y. One output makes a minor index error and returns x plus y plus 1. With self-consistency, we ignore the outlier and confidently select return x plus y because 4 out of 5 independent reasoning paths agreed on it.
Moving on to our next question, how do you use active learning to continuously curate the highest value few-shot examples?
Let's talk about how to continuously refine your few-shot prompts in production using active learning. In a real-world system, prompt space is limited and expensive. You cannot simply throw hundreds of random examples into your context window. Instead, you need a smart data flywheel that selects the highest value examples. Active learning focuses specifically on the model's decision boundaries. When your production application runs, you monitor query logs for instances where the model expresses high uncertainty, such as low log probabilities, or where zero-shot attempts fail. These hard edge cases are automatically flagged and sent to human annotators, who craft the ideal target response. Once annotated, these high-value pairs are stored in a dynamic vector database. When a similar query comes in later, your retrieval system fetches these exact hard case exemplars to guide the model. A common pitfall here is populating your few-shot database with easy, repetitive questions that the model already answers perfectly without examples. That wastes valuable prompt tokens without adding any accuracy. To see how this works step by step, imagine a customer support chatbot. A customer asks a tricky, multi-part question about a rare refund edge case, and the model's output confidence is extremely low. The system flags this log entry. A support team lead reviews it, writes the perfect, policy-compliant response, and saves it to the vector store. The next time a customer asks a complex refund query that hits that vector neighborhood, the retriever dynamically injects this newly annotated exemplar into the prompt, guaranteeing the model handles the edge case correctly.
Moving on to our next question, what is the lost in the middle phenomenon and how does it affect example placement?
Let's explore a fascinating behavioral characteristic of long context LLMs known as the lost in the middle phenomenon. You might assume that if a modern model has a context window of 128,000 tokens, it pays equal attention to every token in that window. However, empirical research shows that attention mechanisms exhibit a distinct U-shaped retrieval performance curve. What does this mean in practice? Models recall information exceptionally well at the very beginning of a prompt, due to primacy bias, and at the very end of the prompt, due to recency bias. But information located right in the middle suffers a significant drop in attention weight. If you supply 10 few-shot examples, examples 4 through 7 will have a weaker influence on the model's generation than examples 1, 2, 9, and 10. The mistake many prompt engineers make is randomly stacking few-shot examples or burying critical instructions right in the center of a dense context payload. When you do that, the model is much more likely to ignore those middle instructions. To mitigate this step by step, consider how you place your examples. Suppose you retrieve 5 relevant exemplars for a user request. You should place your core system prompt and general guidelines right at the top. Then, order your examples so that the most complex, trickiest, or most relevant exemplar is placed as the final example, positioned right before the actual user query. Because that final example resides at the recency boundary, its attention activations remain strong, guiding the model to adhere perfectly to the expected formatting and logic.
Moving on to our next question, how do you effectively combine role/persona prompting with few-shot examples?
Combining role prompting with few-shot examples is one of the best ways to achieve granular, domain-specific behavior from an LLM. While a system instruction sets the high-level boundaries, telling the model who it is, few-shot examples demonstrate how that persona actually behaves in practice. Think of system instructions as high-level directional guidance. If you tell an LLM you are a senior cybersecurity analyst, the model adopts a general probabilistic shift towards security terminology. But that general persona leaves a lot open to interpretation. How concise should the output be? What acronyms should it use? What structured format should it follow? By pairing the persona prompt with concrete few-shot examples, you calibrate exact sentence length, vocabulary, formality, and technical framing. A frequent error engineers make is writing system persona prompts that contradict their few-shot examples. For instance, declaring a persona as an empathetic, conversational customer support agent, but then providing rigid, single-word JSON few-shot outputs. That creates conflicting attention signals. Let's walk through an ideal implementation step by step. In your system prompt, you set the role. You are a senior cybersecurity analyst responsible for rapid threat triage. Next, you provide few-shot examples that match this exact role. Input, port 22 exposed to public internet. Output, vulnerability risk, high. Remediation, disable root SSH login immediately. When a new alert comes in, the model not only adopts the authoritative tone of a senior analyst, but also instantly mimics the concise, high-impact formatting demonstrated in your exemplar.
Moving on to our next question, what is negative few-shot prompting and when should you show anti-patterns?
Let's discuss a specialized prompt engineering technique known as negative few-shot prompting. Normally, when we build few-shot prompts, we only show positive examples of correct inputs and outputs. However, models sometimes develop stubborn hallucination patterns or persistent formatting errors that standard positive examples fail to fix. Negative few-shot prompting solves this by providing explicit contrast. You show the model both how not to do it and how to do it. By presenting an anti-pattern labeled as incorrect right next to the desired output labeled as correct, you create a distinct activation differential in the transformer's attention layers. It explicitly penalizes the bad token sequence while boosting the probability of the target sequence. However, there is a dangerous pitfall to avoid: never present negative examples by themselves. If you only show bad outputs without demonstrating the correct behavior, the model might actually absorb the anti-pattern and repeat the error. Always pair bad examples with their correct counterparts. Let's look at a concrete step-by-step example. Suppose you are building a data extraction pipeline to normalize dates into ISO format, but the model keeps returning relative terms like yesterday or last week. To fix this, you add a negative exemplar. Input, extract date from message met yesterday. Incorrect, yesterday. Correct, July 21st, 2026. When the model processes new inputs, this explicit contrast warns it away from relative date output and forces it to map directly to formatted ISO strings.
Moving on to our next question, how do you test if a model is genuinely learning in context versus relying on pre-training bias?
A crucial question in prompt evaluation is determining whether a model is genuinely learning in context or simply regurgitating facts memorized during pre-training. If you give a model standard examples, like asking for the capital of France, and it answers correctly, you don't know if it read your few-shot prompt or simply pulled Paris from its pre-trained weight memory. To rigorously test true in-context learning, researchers use diagnostic techniques like label flipping or synthetic task benchmarks. Label flipping intentionally modifies real-world facts inside the few-shot context, for example, declaring that Paris is the capital of Japan. If you query the model and it responds with Japan, it proves the model is actively overriding its pre-training memory and following your prompt's in-context rules. If it responds with France, it proves the prompt failed and pre-training bias dominated. A common mistake in production evaluation is testing prompt templates with standard, unflipped data. You end up with a false sense of security, assuming your few-shot prompt is guiding the model, when in reality the model is just relying on memorization. Let's walk through a synthetic example step by step. Suppose we invent a non-existent language mapping. GORP means hello. We build a few-shot prompt, example, input, GORP-output, hello. Then we pass the task input, translate, GORP. Because GORP does not exist in any pre-training corpus, the only way the model can produce hello is by performing genuine in-context reasoning based strictly on the prompt exemplar provided.
Moving on to our next question, what is meta-prompting, and how can a stronger model generate examples for a smaller model?
Let me explain meta-prompting, a powerful framework where we use a larger, state-of-the-art teacher model to generate and optimize few-shot prompts for smaller, cost-effective student models. In production systems, hosting large models like GPT-4o or Claude 3.5 Sonnet for every request can be expensive and slow. Smaller open-weights models, like Llama 3-8b, are significantly cheaper and faster, but they often lack the zero-shot reasoning capability of frontier models. Meta-prompting bridges this gap. We prompt a frontier teacher model to analyze our task, brainstorm complex edge cases, and automatically generate high-quality, step-by-step few-shot exemplars. We can even ask the teacher model to critique and refine those examples. Once generated, we take those rich exemplars and embed them directly into the prompt pipeline for our smaller student model. A major inefficiency in many AI teams is spending hours manually handcrafting few-shot examples. Humans naturally suffer from cognitive bias and often miss subtle edge cases that LLMs encounter in the wild. Let's walk through an operational example step by step. Suppose you need to extract complex nested JSON from unstructured legal contracts using Llama 3-8b. First, you run a single meta prompt on GPT-4 asking it to generate 20 diverse, highly tricky contract snippets alongside their perfect target JSON schemas. Next, you select the top 5 most diverse output pairs. Finally, you embed these 5 synthetic examples into Llama 8b's prompt. Now, the small model performs near frontier-level JSON extraction at a fraction of the cost.
Moving on to our next question. How do structural length variations among few-shot examples skew generation length?
Now let me examine how token length variations across few-shot examples can unintentionally skew a model's generation length. Large language models don't just learn what to answer from few-shot examples, they also infer how long their output should be based on the structural length of your target demonstrations. This happens because the transformer's attention mechanism tracks token sequence lengths and positional distributions across the context. If your few-shot prompt contains example 1 with a concise 10-word output, example 2 with a 200-word detailed explanation, and example 3 with a single-word output, the model's probability distribution for generating end-of-sequence tokens becomes extremely unstable. When given a new user query, the model might produce a truncated, one-word response or ramble endlessly for 3 paragraphs, simply because the target length signal in your prompt was ambiguous. A very common mistake in prompt design is mixing high-level summary examples with long-form detailed examples inside the same prompt. That length variance creates unpredictable response lengths in production applications. To fix this step-by-step, you must standardize the structural length of your exemplar outputs to match your exact production requirements. For example, if you want your final application to generate concise executive summaries, audit every single few-shot example output so that each strictly consists of 2 to 3 sentences. When every exemplar demonstrates consistent 2 to 3 sentence outputs, the LLM receives an unambiguous structural signal, ensuring predictable, highly uniform generation lengths every single time.
Moving on to our next question. What is cross-lingual few-shot prompting and how does it work across language boundaries?
Finally, let's look at cross-lingual few-shot prompting and how language models perform tasks across language boundaries. In many international enterprise applications, you need to process user queries in low-resource languages, such as Telugu, Swahili, or Vietnamese. However, high-quality, annotated training data in those languages is often extremely scarce or non-existent. Cross-lingual few-shot prompting solves this issue by taking advantage of how modern multilingual LLMs represent language under the hood. Multilingual models align concepts across different languages into a shared cross-lingual vector representation space. Because of this shared internal geometry, you can provide few-shot examples written entirely in a high-resource language, like English. The model extracts the task structure, formatting rules, and reasoning steps from those English examples, and then seamlessly applies that logic to a query written in a low-resource language. A major misconception among developers is believing they must translate their few-shot example sets into every native language spoken by their users. That creates massive engineering overhead and management complexity. Let me walk you through a real-world step-by-step example. Imagine you are building a global sentiment classification system. In your prompt context, you provide 3 clear English exemplars demonstrating how to extract sentiment and output JSON. Next, you pass a user query written in Telugu expressing that a product is great. The LLM maps the Telugu query into its shared conceptual embedding space, applies the English task rules, and correctly outputs the classification as positive without needing a single Telugu exemplar.
Excellent. You've completed few-shot prompting, Part 4, Advanced Concepts. In the next video, we'll dive deeper into using one-shot prompting to enforce strict JSON and XML outputs for API integrations. If you found this video helpful, please like, share, subscribe to SHR Trinity, and press the notification bell so you never miss our upcoming AI interview preparation videos. Thank you for watching. See you in the next video.